Hello everyone, this is Learning Objective 3 Exercise 1. We're going to talk about linear regression. You can, as always, download this file from our website, and it includes 3 tabs: exercise, exercise solution, and a question. In exercise, we're going to do the calculation step by step. In exercise solution, the solution is already prepared for you, as the name would suggest. And there is also a tab called question, where you have to replicate the calculation on a similar yet different data set. So let's get to it. We're going to talk about linear regression, and we have here a question. You have collected the data below on incredibly stably included company profits, and you would like to know how the profits correlate or what kind of relationship they have with overall GDP growth. So we have 2 variables: GDP growth and our company's profits for altogether 12 years, and we want to find the relationship. Well, I'll show you altogether 3 ways. One is really simple. The second one is kind of long, but you will see that it actually gives you a lot of understanding of how correlations are calculated. And last, I'll show you one way how to do it even easier than the first one. Yet it will give you much more detailed view into regression, and if it's statistically significant and other things. So let's get to it. So first of all, we can basically just use the chart, which will show us the correlation. So we have 2 variables: GDP growth and profits. We want to know how profits correspond with GDP growth. So the profits in our exercise are independent variable, which we are going to signify as y, and GDP growth is going to be a dependent variable, which will be on x-axis. So first of all, we highlight both of the data sets, or it's a one data set, but each point has has 2 numbers on 2 axes. So we go to insert and to choose chart. We want to use the scatter box, and this is the chart of for in each individual year. We see basically GDP growth on one axis and uh, the profits on the other axis. Uh, we probably want to do some formatting first, so we can choose some of the pre-prepared options in Excel. This one looks kind of nice and scientific, so we're going to use it. And then we probably want to add the axis as well, so we go to design and add axis titles: primary and primary vertical and primary horizontal. And now I just want to copy it in there. And the profits, to double click inside to actually get to the editing mode and copy it in as such. Now we have quite a nice chart, but we still don't see much of the regression. So what we have to do is to click uh, on the data points, all of them. You can see them all highlighted, and then right click and you press add trend line. This nice menu over here opens, which offers you quite a lot of different ways how to plot the trend line. You can go linear, logarithmical, polynomial, so you can basically add any relationship which you think is necessary. But in this case, you can see that the data points are kind of like nicely clustered all around. So linear will suffice. And then the most important thing, you have to add the equation and R square, which is basically the 2 most important properties of the linear regression. And so you can see basically this is the relationship formula, which basically means that the profits are 98 times the GDP growth plus $148, or it's actually thousands of dollars. And the relationship is 93, the R square is 93, which basically means that, even though not everything, not every data point is explained only by GDP growth, but the GDP actually has quite a significant impact. It basically means that 93% of the sales can be explained by GDP growth only, which is kind of impressive. So this is the relationship, and I will show you how to actually calculate it, because here the Excel just did it for us. We actually don't know how we got there. So I have here like a few places already pre-prepared for our calculation. So we'll start with the count. So count is how many data points we actually have. So I'm just going to highlight this whole area, and it's a 12. We can also calculate them like one by one, and we'll get to the 12 as well. Then n minus 1, which sometimes is also called the degrees of freedom. We have one data set, so it's just count minus one data set. Then we have to calculate the averages for both of the variables. So x is the GDP growth. So we'll just use the average function. Average, always choose it from the formulas prepared. Highlight our data points. We do the same thing for profits, our y variable. Average again, choose it, and highlight all of the values for y. And now we would like to calculate the standard deviation, but we can't yet, because we don't really have this area here just calculated just yet. So first we'll calculate the errors, the differences between the average average of the y or x variable, in this case s, the GDP numbers, and the average itself. So it's always the data point. Sorry, I had two equal signs in there. Data point minus the average. And I want to log this second part because I'm going to copy it down and I don't want it to change. So copy it down. And now I can just check if the formula actually works, and works quite nicely. Always this point minus the average. The same thing over here. This point minus average. I will also add the sum, and it should be 0, because if we sum all of the differences from the average, it should end up being 0. So I add it using the sum function, and indeed it is 0. We'll replicate the same thing for y. So again, data point minus average. I again log the second part of the formula using F4 button, copy it down, and copy the average, and 0 again. I'm going to pre-prepare the sums over here. If I just copy the sum function to the right, it just uses the same area but one column to the right, as you can see over here. If I just highlight, if you want to see what the formula is summing up, all you have to do is double click on the cell, and it shows you like by highlighting which formulas were used. Now I want to calculate quickly the differences between x and x bar and y bar. So it's basically just multiplying this formula by this formula. Again, I just copy it down, and it just nicely uses the formulas changed for individual row. Then I also want these differences to be squared. So highlight, use this little roof sign 2, which squares it, and copy it down. Again, you can check that the formulas nicely work. Sorry, double clicking. And I can actually just copy it to the right, and it will do the same thing for this formula, for this column, for this data point over here. And again, copy it down, and now I just quickly check if it does what I want it to do. And I have to really carefully double click on one cell. If you click on two cells in 2 clicks, it doesn't work. And now let's get to the standard deviation. So standard deviation, uh, we have to take the sum of x minus x bar, which we have prepared over here, divided by n minus 1, our degrees of freedom, and that gives us variance, and then we'll have to square it to, derive the square root to get the standard deviation. So I'll start the formula with equal sign, brackets, and now the sum of the differences or deviations divided by degrees of freedom n minus 1, close the brackets, and I want to derive the square root, which I'll give by, nothing happened, I'll just return to the formula, by squaring it at 0.5. And this is our standard deviation. We can also calculate the standard deviation way faster. We'll just use the SDEF function as the def, and there's a few of them prepared. You probably end up using only STDEF-P and STDEF-S. STDEF-S is for samples and STDEF-P is for populations. Well, we have a sample here, so we're going to use the STDEF-S, and it asks me just to insert the the data points, which I'll do by highlighting it and press enter. And you can see that the formula actually delivered exactly the same thing as the long way we did, like using this table over here. We'll do the same thing for the independent variable y for the profits. So again, and I'll actually use a little bit different function here. I'll use square root sqrt, and again it's just the same formula as we used over here, only with y's. So I want to use the sum of the deviations squared divided by the degrees of freedom n minus 1, and that gives me the sample standard deviation. And we'll replicate the same thing using the Excel function stdef-s. And again, just he asks me for the numbers, so I'll highlight the y variable over here, and we'll get again the same standard deviation. Now we'll calculate the covariance. Again, like we have the formula nicely prepared over here, so we'll just follow it. So that's the sum of x bars times y bars, which is this column, this sum prepared over here. So we'll do so by summing, sorry, not sum. We'll just use that that sum over here divided by degrees of freedom. And we can also use the covariance function. And again, we want to use the one for sample with the s at the end. And it asks us for two arrays, so we'll just highlight first the dependent variable, then the independent variable. It doesn't really matter which one you highlight first, but you have to highlight them both. And again, the variance end up being exactly the same number. Now, to get the r, not the r square yet, just the r, what you want to do is, again, follow this formula over here. You divide the covariance by the standard deviations of both y and x. So I'll choose one of the covariances which are the same, so it doesn't really matter. Divided, brackets, standard deviation 1 times standard deviation 2, close brackets, and that's what it is. So this is the R. You might notice that the R now differs a little bit from the R square, which you have over here. Well, it's just because it's not squared. This is that's all the difference there is. So if I just want to check if the calculation is correct, I'll just square it, and there it is, 0.93, 0.93. We calculated it correctly. Uh, as always, this way how to calculate R square or R is kind of roundabout and too long, and it just wastes a lot of time. So we can use different functions. We can either use Pearson function. So Pearson again asks us for the arrays. So one array, second array, and we get exactly the same number as we did over here. Or, and this one is a little bit better and easier to remember, Corel function. Again, array 1, array 2, bang. And again, we get the same R. And we'll get into the end. Finally, we can calculate the slope b1 and the intercept b0, which are basically the coefficients which will give us the linear regression equation, basically the relationship itself. So the b1 is quite simple. You just divide the covariance by variance, which is so the covariance we calculate it over here, divide by variance, which is the sum of x minus x bar squared, which is over here, and there it is. We can immediately, check our calculation by using a Excel function again, and you want to use the slope function. Slope. No y's. Well, y's are the profits, so we highlight them first. No x's. And the result is a little bit different, and I want to find y, because that shouldn't really happen. And this one is probably correct, so we made a mistake somewhere over here in the formula. And I'll just go to exercise solution to actually find out where did I make the mistake. And oh, indeed, why did I divide it by? That's because I want to divide it by the sum. Nope. Once more. So just following this formula over here, uh, the multiplication of the differences minus the differences of x squared. So it's this divided by this cell, and of course we get the same one. That's why it's kind of important uh, to replicate the formula, the calculation a few ways, because it's kind of like provide additional check that you don't make a mistake. It's absolutely normal to make a mistake in a formula. It happens to everybody. So if you do so, you don't have to really feel bad about it. You just have to do the calculation 2 or 3 ways and check that that it's correct. This 98 over here, I know it's correct because it already shows over here in the equation. So I should have actually picked up on my mistake immediately after that. But that's why we show you how to do the calculation so you can check it yourself. Now let's get to the intercept b0. Again, we can use a formula which we can use the formula, which is basically that b0 is x bar minus b1 times sorry, y bar minus b1 times x bar. So y bar minus b1 times x bar. And again, 148, we see over here it's correct. So this time I managed to put the formula there correctly. And we can also use the intercept function. So intercept, no y's, no x's. So incredible profits are y, x's are the GDP numbers, close the brackets, and we got exactly the same number as before. And well, now if we just want to put together the equation, so I can just write y, the independent variable, equals slope, which is 98 times the decimal points 90, also 8, x times, sorry, plus 148.41. And this equation over here should better be the same as the one over here. I differ only in how many decimal points I rounded up or down. So it's all correct. And as you could have seen, this calculation was kind of time consuming, and especially for more complicated regressions, it's really much more complicated than like this. This is still like really simple two variable linear regression, not really so complicated. It still took quite a long time. So I'm going to show you how to actually do it much faster. So first of all, we have to go to data and data analysis. If you don't have this option opened here, you have to go to File, Options, go to Add-ins, Excel Add-ins, Go, and this analysis toolpack needs to be clicked in. If it's not, just click it in and press OK. I already have it clicked in, so I'm not going to do anything and go back. And now I go to Data, Data Analysis. This protocol window opens. You want to choose regression. There's many things you can actually do using this tool, but at this point we'll use the regression. Double click on it. I actually did the regression before, so I already have uh, the fields highlighted, but we'll do it again. So Y range, well, that's the profits. So I highlight it. X range, that's the GDP numbers. Be careful to always highlight also the labels, and I'll show you why. Because here you have to click labels, so the calculation then is kind of easier to read. Then you have to you can choose confidence level. Well, 95, it always automatically calculates the confidence level of 95, but we also want to see 99. Then the output range, we'll choose just under our calculation, so it's correct. And you also want to click residuals, residual plots, and I'll show you why later. Click OK. And there's the calculation. There's the residuals. Residuals are basically the expected number which is given by the regression equation, and difference between the expected number and the real number. So basically the difference of what it is and what the regression would expect it to be. And I'll show you here on the residual plot, which end up being over here for some reason. So I'm just going to move it down and a little bit highlight it. Um, every time you calculate regression, it's really important to look into the residual plot, because the differences between expected and a real number should be kind of normally distributed around the equation. So it should be basically oscillating above and below zero, normally, without any systematic error. If you see any systematic error in this chart, then you know that you made a mistake and you should have probably choose the different regression equation. But in this case, you can see that, the data points, they kind of like a nicely oscillate around zero, and they don't cluster anywhere. There doesn't seem to be any systematic error. So linear equation is actually a good regression. The linear regression really suffices for this calculation. And here, the regression statistics. So first, we got the R and R square, exactly as we calculated over here. you have the intercept and and the slope as well. So the GDP growth, the influence of GDP growth is signified here as the slope, and the intercept is 148, exactly as we calculated here before, just the rounding is a little bit different. But it also calculates the degrees of freedom over here in a nicely prepared ANOVA table, and also, and it's really cool, calculates the p numbers and the confidence intervals. So for any regression, you always want to check basically two things. The p-values, they should be as low as possible, and they are quite low in this case. Basically, if you have confidence interval 95, that means that alpha is 5%, 0.05, and you want the p-value be always lower than alpha. So for the confidence interval 95, I compared this number with 0.05 or 5%. Well, it's lower, and for the slope, it's even lower than that. So we're good, and we can say like straight on that the relationship is statistically significant. We also want to check, and basically that kind of it's the same thing, just interpreted a little bit differently. The confidence interval. For slope, we want to basically see that the GDP growth really has a statistically significant impact on the profits, that the relationship exists. And to do so, depending on how the sample is big, we basically want to calculate a confidence interval which shouldn't include zero, which would mean that possibly the GDP would not have any impact on the profits, which would mean that there is no relationship. And because we already see over here that this confidence interval doesn't exceed over zero, well, that means that at 95% significance, the relationship exists. We can also do it for 99% over here, which is like much higher certainty than 95%. And again, it doesn't exceed over zero over here. So at 99% of certainty, we know that the relationship actually exists. And that's the end of the calculation. So I thank you very much. And so please replicate the calculation for yourself following this video, and then complete the question tab and upload it to our website. Thank you very much, and see you next video.